Hi nerds! I'm being deadlift today with the hi nerds.
Yeah.
Carlos is here today and he's being me with the hi guys. Okay, so Carlos came over today. He has bought himself an oscilloscope, this Hammer Time?
Hanmatech, but
Hanmatech, Hanmatech, can't touch this Hammer Time oscilloscope. 4-channel scope for, how much did this cost you?
Here to Canarias, I paid 179, but the normal price is right about 220
euros.
Yeah.
Okay, so that's the price of this scope. Carlos bought this himself. This is not a product review. Well, it is, but it's not a sponsored review.
Out of pocket myself.
Yeah, out of his own pocket he bought this. So we're going to have a quick look at the scope. Carlos actually did review this on his channel, but we'll have a quick look on here. And then I will make sure the link is in the video description to Carlos's channel.
Thanks.
You can have a good look. And if you want to subscribe to Retro Upgrade while you're over there, I'm sure this guy will really appreciate that.
Yeah, I'm so close to 1,000 subs. I have 960. Come on, guys.
That's not much of a big ask, is it?
No, it's 40 subs. I think you can do it, guys.
Great, great. So when Carlos made a review of this, one of the viewers was commenting about the dangerous to use oscilloscopes on what we call hot ground. This is mains equipment, which isn't mains isolated. At the same time, one viewer on my video I made recently also was asking what is the difference between hot ground and ground. He didn't really understand this term, hot ground. So since I mentioned hot ground and since one of Carlos's subscribers was talking about this, the dangers that we might face using this equipment, I thought we'll also talk about that. And Carlos was saying to me, Rich, can you give me a good explanation of hot ground?
Yeah, because I have used scopes before in university and stuff, but I never owned one. I used some here at Richard's place as well, but I'm not familiar with all the ins and outs, especially the pitfalls. So why not ask the master?
Thank you. Yeah, I work on more mains powered equipment. I mean, Carlos really...
Yeah, video games and low power stuff, 12 volts.
Yeah, and you don't like being connected straight to 240 volts.
I have been. No, I don't like it.
And the games consoles don't either, I guess.
No, usually they have a power brick, external power brick.
So what we have on the screen at the moment, we have Carlos's shiny new can't touch this oscilloscope. And in the inset window, that's actually my Rigol. So this is a 50 megahertz scope. It's never been modified or upgraded. I know you can modify this to be rated at 100 megahertz. And they're both connected to the same thing, which is this item here. So just before we came online to make this video, we were having a quick look to see how well these scopes work.
Yeah.
And Carlos doesn't have an RF signal generator.
No.
And I said, oh, I do. So what we actually have at the moment, what rating is this oscilloscope?
It's 110 megahertz with 1 gigasamples per second. So it's good enough for most things, for hobbyists at least.
Okay, and what we have connected to both of these right now, and you'll see that this is slightly more stable than the Rigol, is this signal generator, this thing. This is a PCB-wave project. You can see it's just a bare PCB on the bench. There's no shielding, so I do get some noise in the signal. But right now, this is generating a 225 megahertz RF signal.
Yeah.
And this 110 megahertz scope is displaying it, although it can't read the frequency.
Yeah, but I can see the Rigol. Surprisingly enough, it's a 50 megahertz scope. It can actually read off the frequency.
Yeah, and saying 222, 287 slightly unstable. And I also have a slightly less stable image. This is certainly synchronizing very well, triggering on that.
Yeah, considering the price of the product, I've seen scopes 5 times the price that actually can trigger at these speeds. So that's really impressive. I'm impressed with the Rigol scope actually, that it can read it off.
On a 50 megahertz scope,
yeah. So you can see on the screen here, it doesn't show the actual frequency on mine. But if you are used to scopes and know divisions and the time steps, you can actually calculate it quite easily.
Correct. In fact, I was saying to Carlos back in the 80s,
Yeah.
that's what we did. I mean, we didn't have readouts on those scopes.
As long as you have a stable signal you can see, you can calculate the frequency and the amplitude and everything.
But from my point of view for repair, I want to know, like, is the thing running?
Yeah.
Do I have a signal at 225? If that's what it is, a transmitter, do I have an output?
Yeah, exactly.
Yeah.
So this is well over good enough.
Yeah, absolutely. So that was just the first thing we have on here. We surprised ourselves. Both of these scopes are actually doing this at way over their rated performance, their specifications. But I'm now going to hand you over to Carlos, and he wants to give you a quick rundown about this scope, what it is, and
what I've actually tested, because I haven't gone through it all. There are a few caveats to this. It's a little clunky to use because it has less knobs, so you have to go into menus and find all the settings. But it's also a full-featured scope, so it has a lot of extras normal scopes for this price range especially don't have. For example, let's go over to the triggering settings. I have special triggering modes that most scopes don't have. Video triggering. So it has NTSC, PAL, and CCAM. So for my work, when I fix video games, usually you have no display, and that means you don't know if it's actually making a signal with sync or it's not. So you can actually go here, and instead of, you can go for sync. Oh, sorry. That's one of the annoyances.
It times out.
Yeah, it times out. Okay. You have sync.
And frame sync.
Field.
Yeah, field or frame, I would call it.
Odd and even.
Yeah.
And you can actually go per line, per scan line.
So you can trigger on a certain scan line.
Yeah, if you know it's at the top, for example, you have a glitch. You see a black piece or a missing pixel or whatever. You can actually go to that line and check what's going on. So if there's noise, for example, throwing it off. So that's perfect for my use case.
Yeah, interesting.
Video triggering is actually a high-end scope feature normally. So that's why I bought this thing, because I was on the fence buying a oscilloscope. 200 euros is still a lot for me because I don't make any money making YouTube videos yet. So this is an investment for me. And I'm going to use this to improve my ZX Spectrum RGB converter. So it converts from the ZX output on the back from YUV to RGB. But I need something to measure the noise. Yeah. So, and then find the noise where it's being introduced and then reduce the noise. And also see if the noise is a special frequency so I can filter it out or whatever. Okay, so let's go over the scope. It has everything you would expect. It has 4 ports, so that's really useful for me because
it's a 4-channel scope.
Yeah, exactly. So 4 channels. I'm not sure if it's 110 megahertz per port. I'm guessing no. Usually it's not, but it can be.
Well, I think we can find this out actually straight away because we're already pushing this above its limit.
Yeah.
But let's reduce the frequency on the generator down to 110.
Yeah, exactly. Okay, and then we can hook up.
And then we can hook up 2 channels.
Yeah, I have all 4 probes. You get 4 probes with this. Also, you get a power supply. It's a USB. This is run through USB without a ground tap, so it's completely isolated. That's one of the things we're going to touch on later.
Yes.
It has a signal generator for calibration. It has triggering, like I said, math functions, so you can subtract and add different signals to each other. It also has measuring functions of different kinds. You can set up utilities. You can even connect this to the PC and export the waveforms and stuff. A problem with the PC thing is I found it very slow. So it's not useful. And another thing to remember, if you connect this to the PC, you are on earth ground. Because you ground through the PC.
Which is something we're going to talk about this hot ground.
So we're going to go through that on hot ground because that's really important, because you can fry this thing if you are not
familiar with what you're doing.
Yeah, exactly.
Yeah, we'll definitely touch on the do nots when it comes to scopes.
Perfect.
So this thing, which is sort of lashed together, has crashed a few times while I'm pressing the buttons. So I'm now on 100 megahertz, and I'm going to leave it on there.
Yeah.
We can still see that both scopes...
We can go for auto here,
okay,
and show how fast it does it. It's a little slow. It takes about 13 seconds to boot up this thing. But you're 13 seconds is not a long time, really.
No.
Let's be honest. And it triggers quite nicely.
And it's now saying, well, 89, 92, 100 megahertz.
Yeah, it's jumping around 45. Okay, so it's because of the noise.
It's got it now.
Yep. Oh, wrong way.
Okay.
This one. There we go.
Okay.
So
you have to turn that quite a few times to actually move that.
It has some kind of speed up. So,
okay.
So the more you turn, the faster it goes.
Okay.
So I went slow. That's why it bugged out. Okay, so it's showing 100 megahertz exactly, practically 110. So
the Ragdoll's showing more of an accurate sine wave.
Yeah, at this speed.
At this speed, yeah.
The faster you go, the better this little thing does. Actually.
Yes, it does actually. Yeah, because this little thing, by the way, is Arduino based. It's an RF generator. This was a PCBWay project. If it was in a metal shielded case, I'm sure it would work much better than it's doing.
Yeah, it wouldn't jump around as much.
But this item, this thing where my finger is, this is an Adafruit module, and it's actually a clock signal generator which they're using to give an RF signal. So in actual fact, at lower frequency, it looks more like a square wave.
Yeah.
So there we are. I've switched my scope off now because I've let Carlos use my scope probe basically.
Yep.
He didn't bring all the ones with him. So we now have both scope probes connected to the signal generator. The signal generator is set at 220. And we do see a trace on both channels there.
Yeah, pretty much the same, especially if you put the position at the same
What
place.
I do notice is a slight difference in phase between the two
so
scans. So it's like he's processing one and it's processing the other.
Yeah, so could that be your probe?
No, I think that's your scope effectively sampling one and then sampling the other one.
Yeah, so it's managing to sample two at a frequency that's way over its rating.
Yeah.
They go down to 100, and so it's inside its, let's say, rated range.
One moment, if I can just get down there without crashing the
interface.
Interface, yeah.
Just to make sure it's actually... Okay, they're going into phase, both of them now. And then they went out of phase.
That's 100.
It went in phase and then out the other way. Interesting.
That's interesting, that, yeah.
So the timing, Okay, so it seems like Richard is right. It's sampling one, then sampling the other, then sampling the other, then the other.
Yeah.
You will always have a time delay of a few nanoseconds.
It looks like that. Obviously, I've not played with this very much, but it looks like that. I don't think we can actually change the horizontal position of one trace versus the other one, can we?
No, I think they are
it's
synced.
for both together. They sync together. Yeah.
Let me see if we push.
It's changing them both at the same time.
If I push the blue.
Okay.
Sorry, the blue and then push. Yeah, no, both at the same time. Okay.
Yeah. Okay, so we've had a little play with the scope.
Yeah, it's good enough for most things, pretty much. That's what I would say. This is not a professional tool for. Yeah, you could use it for professional setting, I guess.
Yeah, you can still use it in the repair setting. That's what I would be using it.
For sensitive work like RF tuning or whatever. No, don't do that. Go buy a real one.
Okay. So that brings us round to this discussion about hot ground.
Yeah.
So I'm going to clear a bit of space on the bench and then let's have a talk about that. Okay, so hot ground. What is hot ground? I mean, that's a very strange thing to say. It's not what you find by a volcano. It doesn't mean molten lava or anything like that.
It doesn't mean it actually heats up.
No, it doesn't mean it actually heats up. But hot ground is something very important. So first we're going to talk about the mains, your mains wiring coming to your house.
Yeah, the 50 hertz.
50 hertz. And we all know over here that is 220 or 240 volts AC.
Exactly.
AC. So with AC, you don't have a plus and a minus.
No.
You have literally AC. And that is coming from a transformer. So we have in the electrical substation, feeding your house, AC.
Yeah.
And both ends of the transformer winding are basically the same.
Yeah.
There isn't a, why do we have a live and why do we have a neutral? Because it's just AC. So if we measure across from here to here with our meter, in fact, let's do it. Let's just prove the point.
Yeah. It should show 220
volts AC. So we'll do that.
Okay,
let's get the multimeter out. Let's stick some probes down the end of here. So we'll go to volts AC. Okay, this is a power lead. It's plugged into the mains.
Make sure your leads are high voltage ones.
Yeah.
If you plug them into mains.
If you're going to do, and then we stick these in anyway. So if we go into here, and here I'm on the volts AC, and we have 228 volts AC. With the black lead here and the red lead here.
Yeah.
If I take that off here and we put the black lead in here, we put the red lead in here, we have 228 volts AC.
It's the same both ways around.
It's the same.
That's why you can plug in a plug either way.
Yeah. In some countries you can't.
Yeah, English plug. You have.
You can't. Yeah, but this is our mains plug, and you can plug this in either way.
Yeah.
Okay. So live and neutral are not really parts of the concept of AC. For example, if you take a piece of equipment, whether it's a TV set that uses mains or a hairdryer or anything else, and you plug it into the mains, no matter which way round you plug it in, it will work.
Yeah.
Okay. So basically, both ends of this transformer winding coming into your house from the substation are the same.
Yeah.
So why do we have live and neutral? Because we all also know that we can touch the neutral wire and we'll be okay.
Yeah, but
and if we touch the live wire, we'll get a nasty shock.
Yeah.
Right. The reason for that is because these wires come into your house, okay, to your power socket. So this is your power socket in the wall. Okay. At the substation, one of these wires is connected to earth.
Yeah.
That's a big metal rod stuck into the ground.
Yeah, they literally hammer it in.
Hammer it in, yeah. So that end is what we call the neutral end. So although we have an AC signal here, one of the wires is already connected to the ground at the substation.
Yeah.
And you'll also notice in your house as well, you have an earth terminal. And that's also by your door or by electricity meter. Got a nice big metal rod stuck into the ground.
Yeah, and they do the same at the power station.
And the same at the power station. That's this thing here. So what happens now? When you come along as a person, we'll draw you. So this is you standing here. Okay.
Not bad.
Not a very bad person or not a very good person. Okay. And you take your finger. And you touch neutral. Where are your feet? Well, you're
on the ground.
You're on the ground. So you are forming a circuit path from here through your arm, through your body, through your legs to ground.
Yeah.
But this wire is already connected to ground.
So it will take the path of least resistance.
And that way you will not get a shock by touching this. Okay, there's quite a lot of resistance in the wire coming all the way from the substation.
True.
So there may be some residual voltage on here, but not very high.
You can get a shock.
Yeah, but not a powerful one.
You can. It won't kill you instantly. Let's say that.
So if you now get your partner, you ask her to touch that wire. This is the live wire, and she's standing on the ground. You will now get a shock because you've got a path for the AC to go through your finger, your arm, your feet.
And back to the power station.
And back to the power station on the ground. So that's why we have live and neutral.
Yeah.
Now you might ask yourself, if that's the case, if this isn't connected to the ground at the power station, then you could touch either that one
or the other one.
Or that one, and you wouldn't get a shock.
True.
And the reason being because this winding in the power station is now floating.
Yeah.
There's no connection to ground. So if you come along and you touch this one, yeah, and you're standing on the ground, this end of the winding automatically becomes the neutral end.
Yeah.
Because you were connecting it to the ground, and the other end is now 250 volts away from you. Yeah.
So you make the ground.
You make the ground. If you take your finger off here, so you're not holding on here anymore, and you touch this one, this end becomes the neutral end, and that end becomes the live end.
Yeah.
Because again, you were standing on ground, you forming the path to ground.
Yeah, the only way you can get a shock with that system is if you touch both ends at the same
once.
time.
Exactly. So you may wonder, why do we have the neutral wire bonded to the ground in the first place? And we actually wondered that as well. We were just discussing the various reasons, and you thought, you know, let's just go look this up. And it turns out basically it's for historical or possibly hysterical reasons.
Hysterical reasons, yeah,
because in actual fact, it is more dangerous having one end of the transformer grounded, because if you contact one end, you will definitely get a shock, another one you won't. Whereas if it's floating from ground, you can touch either end. It doesn't effectively though help you if like you were touching one of the wires standing on the ground and somebody else at a different outlet, or possibly even in the next house or somewhere is touching the other one that's standing on the ground. Well, you know what, guys, we're not going to try it.
No, we're not.
Okay, so we know anyway, because the way that the system works, that if you touch the live conductor, it's going to hurt.
A lot.
A lot. Okay. So this now brings us down to things like switch mode, power supplies. This thing, okay? And what we have here, this is the high voltage side. So we have live and neutral coming in here. We have a bridge rectifier here, which converts that from AC into a pulsed DC. And we have a large capacitor here, which smooths that DC. And this charges up to a high voltage. So this part of the circuit is converting from AC to 20 volts to DC at about 320 volts, which is the peak of the AC waveform, okay? This capacitor then is holding the current which powers this chip, and this chip with its MOSFET switches the high voltage through this transformer on and off very rapidly, and out on the other side we get high frequency AC, and we have another rectifier diode, which on this one is going to be this thing.
Okay, there we go.
And that then converts the AC back into DC again at the lower voltage. And these are your smoothing capacitors.
Yeah, that depends on the turns inside the transformer.
Exactly, the ratio of the turns. And we can see this part of the circuit
is live. Or
that's why it has a line drawn around it, because this is not isolated from the mains. This is connected directly to the mains. And this side of the circuit is isolated from the mains by this transformer. So there's no connection from this side, the primary, the high voltage side, to this side. The only one connection, say there's none, there is one, that's this thing here.
It's the
opto isolator.
But it's isolated.
It's isolated. So this little device, although it appears to be connected between the two sides, this side of it has an LED built in, and this has a photo sensor, a photo transistor in it, and the LED shines a light on the transistor to send a signal. And what that signal actually does, it tells the chip when the output voltage is correct.
Exactly, so it can balance it.
I'll just draw this out, and this is going to explain hot ground. What I've just described then. So we have the live and neutral coming in, and we know why we have live and neutral now. Okay? The live and neutral go to the bridge rectifier. This is made up of 4 diodes. I'll just draw them. They go like this.
This is a full bridge rectifier.
This is a full bridge rectifier, and this converts the AC 240 volts, okay, into DC. I have to remember when I'm drawing these which way to draw them, so I'll just do it now, like so.
I'm impressed you can remember this.
Like so.
Yeah, that seems right.
This is correct.
Yeah.
So this is the bridge rectifier, and what actually happens is, imagine we have a sine wave coming in, going positive and negative, okay? On the positive half cycle, this end is positive with respect to that end, okay? The diode's conventional currents, pass current, positive to negative.
Yeah.
So the current will flow through this diode into this is where your large capacitor is.
Yeah. That's a moving capacitor.
Yeah, and also this is our load, the thing that's drawing current, okay? So the current flows through this diode, into the load, back out to the load, yeah? This end, when it gets to here, look, we've got two diodes.
Oh, okay, yeah.
It can go both ways, but it can't go both ways. And the reason it can't go this way is because this end is a lower voltage than that end is.
Okay, yeah.
This is the positive of the AC. So it has to flow the other way to complete the circuit through that diode and to neutral. So that's the circuit path, okay? Through this one, through the load, through that one to neutral.
Yeah.
Okay? When this end is the more positive, yeah, than that end, when it
when the sine waves goes
the other way, yeah, what happens? The current now flows this way through this diode because it's forward bias, positive and negative, yeah, into the capacitor. Look, it's in the same direction here.
Yeah, in the same direction.
Through the load, same direction.
And then the return path goes the top way. Okay.
Yeah, then the return path goes that way.
Okay, yeah.
So on this side of the bridge rectifier, the current's alternating direction. On this side, it's always going in one direction.
And because it's a full bridge, it takes all the peaks and adds them together.
Yes, so what actually happens is that the path I drew with the blue arrows is that one, and then
and that's the neutral.
that's
That's
the other half cycle.
Yeah, exactly.
So the frequency here is 50 hertz, okay, and the frequency of the pulses here is 100 hertz.
Yeah, it doubles it.
It doubles it, but you won't see that while this capacitor's here because this capacitor charges up to the peak.
Yeah, and it tries
voltage
to keep
there,
it there.
and tries to keep it there. And the peak supply, if this is 240, that's like an average of voltage. It's changed all the time. The peak voltage is around 320 volts.
So peak to peak, 240 input, and the output from a full bridge rectifier is
no,
320.
240 isn't peak to peak. This is what's called the root mean square. It's what we can call the average voltage. But if it was really average, think about it. The average voltage during this half cycle is somewhere sort of there, yeah?
Yeah.
The average voltage here is some sort of there in the opposite polarity. So in actual fact, the average voltage of an AC is 0.
Yeah.
Tell your finger that when you touch it.
No, the finger doesn't agree.
The finger does not agree with the average voltage. So, yeah, call it how you like. But basically, the 240 is that sort of voltage, which is about 65% roughly of the full voltage. It's not 66, it's something similar to that, okay? And the peak voltage is 320.
Yeah, okay.
Okay?
Fair enough.
Which, again, is like another third.
Yeah.
I'd say it was about 66%, yeah?
Yeah.
Okay, so that's what we have. Now, on our power supply, let's say we want to look if the power supply is working with our scope. So we have a transformer here. We have a MOSFET or transistor here. And then that will come back to probably through a current sense resistor, a low value resistor, to there. Okay? This here is being switched by the IC that I showed you, switching on and off very rapidly.
Yeah.
If we want to measure with our scope to see, is this IC working? We need to attach the ground of our scope. Somewhere. And the most sensible place is the negative end of this capacitor because voltages are always relative. There's no such thing as a positive voltage or a negative voltage.
Yeah, really. No, there doesn't.
Voltage is potential difference. It's the difference in voltage between 2 points. And depending on which way round you put your meter,
You get negative.
Positive or negative.
Yeah.
But in actual fact, this positive and negative is just a human concept. It's not really...
No, it's just potential.
It's just potential and potential difference, okay? So we need to put our oscilloscope ground somewhere. And the sensible place where you're going to put it is like the negative end of all the capacitors.
Yeah, that's what you normally think you should.
That's what we normally do, because if you look on the output of here, so this is our output diode, smoothing capacitors, yeah.
Mm-hmm.
This would be our, for example, 12 volts.
Yep.
And this would be 0 volts.
Yeah.
And you put your ground of your scope there.
Yeah.
And then you will see here a positive waveform.
Mm.
Yeah? If you put your ground here, which you could do, you'll see a negative waveform there.
Yeah.
It's all relative, but most people's brains work in a positive manner.
Yeah, they want to put ground to 0 volts. Normally.
Yeah. So we would want to connect our ground to here.
Mm.
Okay. There's two problems with this.
Mm.
One is, if our oscilloscope, okay, this is your oscilloscope, this is your lead. If our oscilloscope is grounded,
Yeah.
so we have an earth wire. So connection to our oscilloscope, we have an earth wire.
Yeah, because neutral is grounded.
No, not neutral. We have live.
No. I mean on the power station.
It is, but we have 3 connections going
Yeah.
to our scope. Even here, we have live, neutral, and earth.
Yeah.
Okay. On English plugs,
It's a little bit different, but same.
you have live, neutral, and earth. Yeah, and earth is connecting to the metalwork of your scope.
Yeah.
The reason for that is because if we connect something to our scope and we clip the ground lead of our scope onto something, this scope now will be at the same potential as that. It's connected to it.
Yeah.
Any metalwork, like for example,
Yeah.
possibly that one, although
All the connectors are bound together as well.
that's
so.
yeah. This actually shows this. So this is a test signal, and that one is ground.
Yeah.
So if we attach this to our circuit here, this point is now connected via
The ground lead.
the ground lead to our oscilloscope.
Yeah.
Now, one of two things will happen, because this point isn't ground. Our oscilloscope, if it has a ground on the mains lead, is grounded. So you'll now connect this point to ground.
Yeah.
Yeah. What that means is that in your bridge rectifier, on the positive half cycle, okay, via this diode, via the load, it's now going to ground.
Yeah.
So you've shorted that point to ground on every positive half cycle.
Yeah.
Yeah. And on the negative half cycle here, when this end is positive, yeah,
Yeah.
the same thing happens through this diode, through the load,
And go down. Yeah.
to ground. So what you're doing is you effectively, on each half cycle, you're shorting one end or the other of the mains to ground. That will blow up the thing you're testing and or your oscilloscope.
Yeah, depending on the oscilloscope design, but yeah.
Right. Now, if your oscilloscope isn't grounded, so it just has live and neutral,
Yeah.
or in the case of your scope,
It has a USB plug.
it has a USB plug, so there's no ground. This is isolated from ground.
Yeah.
What will happen now is this is no longer grounded, okay? But when you attach your scope probe, whatever this is clipped to, for example there,
Takes that voltage.
that voltage will appear on any metalwork on your scope. For example, that. For example, these.
Yeah.
All these points which you can touch,
Yep, you can get a nasty shock from that.
yeah, they will now be connected to the bridge rectifier. Yeah. And look what the bridge rectifier does. We just said it, and we'll say it again.
Yeah.
This point here, half the time, is connected to live.
Yeah.
Another half the time is connected to neutral.
So you will probably get a shock every,
Well, so
50 hertz.
back in the day, in the 80s, when they taught me this was called half mains.
Half mains. Yeah.
Half mains potential.
Yeah, because it's half the time.
It's yeah. What they mean is all of the mains potential for half of the time.
Yeah.
Yeah, because half of the time it's connecting to the neutral,
Yeah.
which won't give you a shock. Another half of the time it's connected to the
But
live, which will give you a shock.
it
But it's
switches-
doing this at 50 times a second.
It switches so fast, yeah, you can't react.
Yeah, you're going to get a shock. So this point is ground in as much as it's our point of reference. So if we want to measure any voltage on here, one end of the multimeter will go here, the backlight, and we'll probe elsewhere. If we want to measure that voltage, 320, backlight here, red lead there. So it is ground in as much as it's a 0 volts reference for our circuit.
Yeah.
But it's not ground in as much as it's connected to safety ground.
Yeah.
So basically, that is hot ground.
Yeah, so it's ground that's in reference. It's reference ground, but it still has voltage in it. Pretty much.
Yeah, yeah. But what you are measuring with your scope probe is the difference between there and wherever this is clipped on.
Yeah.
Okay. So if that end is going up 50 times a second from 0 to 300 or whatever, 0 to 220, on this one here, you'll have also going from 0 to 220, plus superimposed on that the signal you want to see.
Yeah. So
Yeah.
the scope will see the signal.
scope will see the signal. We're going to do this in a moment. The scope will see the signal you want to see. But in actual fact, what's happening is the ground lead of the scope is doing that.
Yeah.
Okay. And the signal you are doing is also doing that, but the signal is on top of it.
It's traveling on, yeah, superimposed on it.
Yeah, yeah. But your scope shows the difference between the two. So what you'll see is a signal.
Yeah. Yeah, it shows the difference. Yeah.
Exactly. So let's do this now. I'm going to show you that we can do it with this scope because it is isolated from the mains. It won't blow anything up, but it's dangerous to do it, and I'll show you how to do this safely. So guys and Carlos, we have the power supply here. So I've connected your scope to hot ground on the end of this capacitor. The other end is connecting to this little inductor. This actually goes to the switching MOSFET inside this chip, which is driving this transformer. I've attached a load because the power supply won't run without a load this one. Okay. We have the scope probe attached. It's set to 10 times on the scope probe. Yeah.
Yep. It is.
We're on 50 volts per division because it's going to be quite a big waveform. It's at mains voltage.
Yeah.
So we're now going to plug this in, start the power supply.
No bangs.
Oh no, nothing went bang. How do we get this? Is this the auto?
Yeah, just press the auto and let it do its thing. Usually it hooks on quite well. It took a while.
I'm still thinking about it.
No, it's not loading.
Oh,
Oh yeah,
okay.
it is. It is.
It is loading. I'm sure this power supply is running.
Yeah. Ah, there we go.
And there we go. So
Oh, okay, so it switched on all the other channels. Oh, wait.
now be careful because your scope is now at half mains potential.
So there we go, and yeah, okay. So just turn,
The time base?
yeah, and probably the steps as well.
The
but-
amplitude of this one?
yeah. There we go.
So we now have a very big waveform. That's the switch mode power supply running.
Yeah.
Now, we're doing that because this scope is running through a power supply USB.
Yeah.
Don't attach it to your PC while you're doing this.
Yeah, this has a connection to the PC, and if you connect it to the PC, you make a ground path through the PC. So you actually make it you make it isolated and non-isolated.
No, non-isolated.
Yeah.
So you'll now connect the switching MOSFET on here to ground. Okay, so that's doing it, but the problem is that the metalwork on your scope is now actually on this about 45, 46 volts.
Yeah.
That's probably not enough to give you too much of a shock, but that is AC, so that's more like 60 volts.
Yeah.
Yeah. So we have a high voltage on the metalwork of your scope.
Yeah.
And that is the problem with doing this. So I'm now going to show you a safer way to do this without having your scope metalwork at a potentially lethal voltage, okay? as I mentioned before, what we're really trying to do here is to display the difference between the voltage on this point and the voltage on that point.
Yeah.
Now we can do that without connecting this ground lead, in actual fact. Now there's two ways to do it. One is with something called a differential oscilloscope probe.
Yeah, I've
this is
seen those.
made specially to show the difference between the two. But there's a poor man's version of this as well.
Yeah,
So
differential scope probes are really expensive.
they are probably as much as this scope.
More.
Okay. So what we can do is, if we just take another scope probe, I have another one here.
Yeah.
I have plenty of these things. We can attach this scope probe to hot ground. I have no earth wire.
The ground wires are not hooked up.
They're not hooked up at all, okay? So this probe is going to monitor the voltage here, and that one's going to monitor the voltage there.
Yeah.
And what we'll have on here is the same as this, plus the signal on top of it.
Yeah.
Your scope has an option to display mathematical functions, yeah?
Yes, it does.
And it has an option to do subtract.
It does.
So if we subtract the voltage on this from the voltage on that, what we will see is the difference between the two.
And you will see the waveform.
Which is effectively what we were trying to do. So can you set your scope to do it? So we need the maths function.
Math.
And we want to have, I'll tell you now, we want to have channel 1 minus channel 2.
Okay. So purple is the math function, pretty much.
Purple is the math function. Can we get it to display just the one we want to see?
Yeah, I'm guessing so. This is the part where I don't know exactly how to get around
Well, we
that.
certainly can see that it's running.
Yeah, so
And I'm sure if Carlos knew how to set his scope, he would know how to do it properly.
so this is a user error.
Okay. As Carlos hasn't figured out how to operate that function on his scope yet, I'm actually showing you on my Rigol. So on here, I have an option for math. Okay. And you can see that I have an operation, so I can have A plus B, A minus B, and various other options. Okay. So I'm actually set to A minus B. Channel 1, which is the yellow trace, you can see that jumble of mess, that's actually connecting to the output of the switching chip, on the inductor. And then channel B is connecting to hot ground. That's the cyan trace. Okay? If I now switch off channel 1 and channel 2, what I'm left with is that violet trace, and that is the difference between the two.
Yeah. So my scope showed the signal, but I couldn't remove the other two superimposed signals.
And there you have it.
So
Yeah,
it does work.
absolutely. So we are now showing the waveform of the switching circuit without connecting to ground at all.
Yeah.
And you can see it works just as well as connecting your scope, which is isolated, to hot ground.
Yeah, it does the same job.
Yeah. So guys, you don't need to do anything dangerous with your scope connecting to hot ground. You don't need to get an expensive differential probe. As long as your oscilloscope has a math function, and you may have wondered what that was for.
Yeah. I have a few other uses for it.
Okay,
Yeah.
but that's one good use for the math function. So look, you can work on this high voltage equipment perfectly safely without connecting to ground at all. And that's what I wanted to show my friend Carlos, because I value my friends and I don't want him to electrocute himself.
Really useful, and I don't have to spend 350 euros on differential.
Yeah. Well, until Carlos reads the manual, I'm actually going to show you another way to do this safely as well. So if we switch this power supply back on,
Yep, I will. Here we go.
we take the scope probe, and I've set it to ×1.
Yeah.
Okay. Can you set the sensitivity of channel 1 to something like, a few millivolts? Put it under a sensitive range.
Should I have it to X?
No, AC or DC won't make any difference.
No, times 10.
If you want, or ×1.
Okay, let's
×1.
times that. What? Oh, okay.
Okay, ×1. Can you set the sensitivity to somewhere into the millivolts?
Yeah.
So I think at the moment, millivolts per division.
Yep, let's go down there.
Right, we're now on 200 millivolts per division. So what I'm going to do now is take the scope probe, not attach it to the PCB at all, but just hold it close to the transformer. Okay? So
that's the same waveform.
that's the same waveform, and I'm not even touching anything now. Yeah, I'm not connecting to it at all.
Inductance.
Yeah, so this, because I have it set to ×1, it'll probably work on ×10 as well.
A little smaller,
A little
but
bit smaller, ×1. So we're not actually connecting to anything on the power supply now, and we can still check that it's running. So guys, that's another way you can do it.
That's a really handy tip. I
Impressive,
like that. Yeah. I didn't know that. That's brand new for me.
And I hope some of you guys out there have learnt that one as well. So the guy who commented on your video originally, which brought this one about,
Yeah.
he was actually correct, but you don't need the differential probe, which is what he said you should buy. And the guy on my channel who asked about hot ground and what it is, I hope that explanation now gives you at least some idea.
Yeah, and it helps me a lot to keep safe. And I don't want to blow up the scope. I like it.
Exactly. So you go and read your user manual.
Yeah.
Yeah. The rest of you guys, hope you enjoyed watching that. Get into the comments below. Let us know what you think.
And if you want to see more about the scope, just go over to my
I
channel.
will link it from this video. Oh, and Carlos needs 40 more subscribers.
Yeah.
Okay, guys. So thanks for watching. See you all soon.
Bye,
Ciao for
guys.
now.